So the next type of CPU architecture or CPU organization is called as the accumulator CPU. Okay. So let's understand how the accumulator CPU works with a simple block diagram like this. You have your CPU, you have your main memory here. By memory, I mean the main memory, or most likely in most real world situations, it's going to be a RAM. Right. So imagine I have a program like this, which consists of 3 instructions, right? So let's understand each of these instructions one by one. So that we understand how the accumulator CPU itself works, right? So we start with the first instruction. It says load 2080. So what it does is, whatever is the data stored, whatever is the actual data stored in address, let's say 2080. Okay, whatever data is stored in address 2080 is now copied to the accumulator. So what does this do? This basically, accumulator equals to the value stored in memory address 2080. That's what it does. Okay, so this command or this instruction does this. Remember, here we are not saying explicitly to load into accumulator, but by default this type of command or this type of instruction will load it into accumulator. Here comes the most important instruction here. Look at this. Here we have an arithmetic or logical operation here, mul, which means multiply. Now what this does is very interesting. So mul 2090, basically what it does is, again here when I say accumulator CPU, we are talking mostly about how the ALU functions. Look at this. In the previous case, when we talked about stack CPUs, we talked mostly about how the ALU itself works, how the ALU uses the stack to store the operands, right? So here also, when we're talking about accumulator CPU, our focus is mostly on the ALU itself, right? So this instruction is very, very important. Look at this. We have mul 2090. So what it does now is it multiplies, because what are the inputs to the arithmetic logic unit? The accumulator is one input. The temporary register is other input. The temporary register is connected to the main memory. Similarly, the accumulator is also connected to the main memory. The temporary register is also connected to your general purpose registers. These are your general purpose registers like A, B, C, etc., etc. Right? So what this says is, whatever is there in the accumulator. So what this does is, accumulator, so the function it computes is, it computes whatever is the value in the accumulator, it multiplies it with the data that is there in memory address 2090. So this multiplied by memory address 2090. The exact steps that it, see, look at this. It performs the arithmetic operation of multiplication on the value that is stored in accumulator and whatever is the value that is stored at memory address 2090, and stores the resultant in the accumulator. Right? In this CPU architecture, there is only one accumulator, right? So there are other accumulator CPUs where you could have multiple accumulators. Let's talk about the simplest case first, right? So now look at this. So this is called accumulator CPU because for all arithmetic and logical operations, look at this, for all arithmetic and logical operations, the first operand is always in the accumulator, and the result of the operation is always stored back into the accumulator itself. That's why this is called as accumulator CPU. The second operand, look at this. This is your second operand, right? Your second operand for the multiplication operation. Your second operand could be in memory. If it is in memory, it is copied into the temporary register and then fed into the ALU. Or it could be in any general purpose register. So instead of saying mul 2090, we could have said mul A. Mul A, what would it do? It would take the value that's in the accumulator, multiply it with whatever value is there in register A, and paste the final resultant in the accumulator itself. So this address location, look at this. This is called a one address instruction. This is called a one address instruction. Why is it called a one address instruction? Because this is my opcode, right? This is my opcode. And my operand, in the operand, I'm giving one address location. This could be the address in memory, or it could be the address of a general purpose register, right? It could be both of them. So typically in accumulator CPUs, the accumulator has the first operand to start with, and The second operand, we can either give the memory location like in this case, or we could give the general purpose register name where the second operand is located. Very simple, right? So what happens by now? Accumulator equals to accumulator into M 2090. Here let's just simplify and say that whatever data that is stored in memory 2080, let's call it as A, just for simplicity. Whatever data that is stored in memory address 2090, let's call it B. Okay, whatever is stored in memory address 2096, let's call it C, just for simplicity. Now let's look at the third instruction here. What does the third instruction do? This is also a one address instruction with the arithmetic operation add as the opcode, and the address is 2096. So what will happen here? My accumulator now will be equal to, again, here also my first operand I'll assume is in the accumulator. So accumulator plus whatever is stored in 2096. So what is the final resultant of these three steps? Let's look at the final result of these three steps. So let's assume the data stored in memory address 2080 is A, memory address 2090 is B, memory address 2096 is C. So what happens now? Look at this. My accumulator initially is A, right? Then I did A into B, stored it back into accumulator. So I performed A into B. Then to A into B, I added C. This is the final value that's in the accumulator, right? So again, if you notice, this is exactly the same operation that we have performed even here. Look at this. What is the operation that we performed here? A star B plus C. The same operation we have done. Here we are using the stack CPU, and hence it requires more instructions. Here we are using an accumulator CPU, hence we require fewer instructions. That's one of the advantages of accumulator CPU over stack CPUs. Okay, very simple. Now if you look at the instruction cycle itself, let's look at instruction 2. Let's look at this multiplication instruction. How does it actually work? The instruction cycle has two components, the fetch cycle and the execute cycle. The fetch cycle, basically what happens in the fetch cycle, this is what is there in memory initially, mul to 2090. So in the fetch cycle, this whole, let's assume this is 1 byte, and let's assume this is stored in 1 byte. Let's just say this could be 1 byte or 2 bytes or 3 bytes, depending on the memory size and the bus size. Okay, just for simplicity, let's assume this is 1 byte, and again, if this is hexadecimal, this requires 2 bytes, right? If this is hexadecimal, this requires 2 bytes, right? So let's assume my opcode is 1 byte, my address is, let's say, 2 bytes. This whole 3 bytes is read from the memory. So in the fetch cycle, this whole, both the operand and the opcode are read from the memory in the fetch cycle. Simple, very simple concept there. In the execute cycle, first this opcode is interpreted. I understand that my opcode is mul, and since I am an accumulator CPU, my first operand is in the accumulator for sure, but I also need to obtain my second operand, which is stored in memory address 2019. I interpret the mul, right? So first I'll interpret it. Next step, what I'll do here is, whatever is there in 2090, I'll copy it to temporary register. Then I'll just multiply within my ALU. When I multiply, one input comes from accumulator, the second input comes from temporary register. Whatever is the resultant, I'll store it back into the accumulator. That's step 4. So there are 4 steps: interpret, copy from memory to temporary register, perform the actual arithmetic operation of multiplication within the ALU. 4th step is the resultant, store it back to the accumulator. This is how your fetch and execute cycles exactly work. Here I'm not going into the details of fetch cycle because we have discussed this, because the fetch cycle is not very different between accumulator CPU or your stack CPU. And we have discussed about the fetch cycle in lots of details in the previous video. The execute cycle is what changes between different CPU organizations. Right? Very simple concept here. Now there are a bunch of examples, historic examples of CPUs which are accumulator CPUs. These are microprocessors, or these are processors from the 40s and 50s. Every one of you must have heard of this computer called ENIAC, one of the first modern computers, right? The ENIAC was a sort of accumulator CPU. ENIAC was built almost at the end of Second World War. It had 20 accumulators, right? What we have seen is a simplified model with just one accumulator, but I could have multiple accumulators where all the temporary results also I'm storing in the accumulators, right? So ENIAC was one of the very first modern computers that was built, and it was a it was an accumulator CPU with multiple accumulators. Similarly, the early computers in the 1950s, named as IBM 701, IBM 650, PDP-8, these are some of the earliest computers. These are examples, these are actual examples. Again, today we have more general purpose computers, or so what we have to, again, we don't use accumulator CPUs per se much, but if you look at 8085 and 8086 processors, there are some instructions where we take the operands from accumulator and we perform some operation, store the resultant in the accumulator. But they're not fully accumulator CPUs. There may be some instructions which are very similar to accumulator CPU instructions, but they're not full-fledged accumulator CPUs because they have many more registers and things like that, right? So what happens here is, again, this is an old school technology from the 1950s, 40s, maybe to the early 60s, but it's important for us to understand these different architectures or organizations so that we can better appreciate the current organizations. Okay, again, the current organizations are very powerful, they're very general purpose, and they're super duper powerful, literally. They're called as general register CPUs, right? So what we use right now are called as general register CPUs. Again, there are multiple types of general register CPUs themselves. Most microprocessors that we use, again, we'll learn about general register CPUs in the next video, right? But even in general register CPUs like your 8085s, 8086, you have some type of accumulation that happens through the through your accumulator register. Okay, we do have the accumulator register even in modern CPUs. So there is some takeaway from accumulator CPUs that we still use in modern general purpose CPUs, but it's just one component. General purpose or general register CPUs are much more powerful in general. Okay, so again, we have learnt about the one address instructions here. You have the opcode and you have the address, right? The address is either the memory address, it's either the address in main memory, or it's a register address, right? It is some location where data is stored, and there is only one. So this is one address instruction because I have the opcode and I have only one address, because the other operand's address is by default accumulator, and the value that I want to store everything back is by default the accumulator, right? That's why I just need one address instructions, right? So let's look at, okay, oh, this is a very nice example actually. Imagine I have an accumulator CPU, right? Suppose if I want to compute this, let's just assume that A, B, C, D are some memory locations, just for simplicity. Instead of writing memory locations, we just wrote some numbers here. Let's assume A, B, C, D are 4 memory locations, and I want to perform this mathematical operation, add them, divide this addition, right? So this will be computed first, this will be computed first, their results are divided. So this whole thing is divided by this whole thing. Now the whole resultant has to be stored back in X. Let's assume X, A, B, C, D are either register names or they are memory locations, right? So let's just assume that they are memory locations, general memory locations. How can I compute this? One way of writing the program is as follows. Let's see this program. I'm loading A, cool. Load A basically means the accumulator will have A now. Add B. So the moment I do add B, what happens? The accumulator will have A plus B now, right? Because A was already there in the accumulator. Add B basically means A plus B will be in the accumulator. Then I'm saying store T, which means whatever is there in the accumulator, store it in T. So what happens now? My T equals to A plus B now. Okay, see, look at this. This arrow mark basically means whatever is the resultant of this is stored in the accumulator. That's what I mean. Okay, so this now what happens? So let me erase this. So your T, again, T is in another memory location. So whatever is there, store T, basically what it does is whatever is in the accumulator, it stores it in T. So within T, I'm storing A plus B's result. Then I'm loading C. So accumulator has C, add D. So what happens now? By this, accumulator has C plus D. Now this sum, I'm storing it in Y. So what happens? Y is A plus B. Sorry, Y is C plus D. I'm sorry. Okay. Because store Y here, whatever is there in the accumulator gets stored in Y. So Y contains C plus D. Now load T. So what happens? Accumulator has T. Accumulator has T, which means accumulator has A plus B. Right? Div Y. So whatever is there in the accumulator divided by Y. So what is there in Y? Y contains C plus D. Right? This resultant, I'll store it back into the accumulator. Now it says store X, which means X will now contain A plus B by C plus D. How many instructions did we need here? We needed 9 instructions. Look at this. This is one way of writing the program to compute this mathematical operation or this mathematical expression. It's not one operation, it's an expression, right? So this is one way I can write a program. But there is a more efficient way I can write it. Here I needed 9 instructions. We actually can solve and compute this result using just 7 instructions. If we actually see here, what did we do? First we computed A plus B, stored the result, then we computed C plus D, stored the result, and then we computed A plus B by C plus D. But what if we do slightly differently? First, what if I load C? Look at this, load C, add D. So what does the accumulator contain now? The accumulator contains C plus D now. So first, see, in this case, I'm first performing this operation, then this operation, then this addition operation. Here, first I'm performing the second addition operation. Okay, then it says load T, right? Then it says load T, right? So what happens now? Actually, this should be store T, not load T. I'm sorry. So this I should store it into T. This is not, okay, so store T. So what happens here? Into T, I'm storing C plus D, whatever is there in the accumulator, and the accumulator consists of C plus D. This should be store. Then I'm saying load A. So accumulator consists of A. Then I'm saying add B. So what does the accumulator consist of now? The accumulator has A plus B. The accumulator has A plus B. In memory location T, I have C plus D. Then it says div T. Because the accumulator already contains A plus B, which is the first operand of this division. Look at this. This is my division, right? This is my first operand. This is my second operand. My accumulator already contains the first operand, right? So if I just say div T, what happens? A plus B divided by T. What is T? T is C plus D. This value goes into my accumulator. So this results in my accumulator being equal to A plus B by C plus D and store X. So which means into my X, I'll get A plus B by C plus D. So here, what we have done here is, we have computed C plus D, stored it in T, and then we have computed A plus B, because A plus B is the first operand that I need in the accumulator. Now here I'm not storing A plus B into memory the way I have done here. Here I've stored A plus B into memory, I've stored C plus D into memory, then loaded both of them and then computed the operation. Here what are we doing? We are first finishing off with C plus D, storing it in a memory location, then we are computing A plus B. This is already in the accumulator. Okay, because this is division operator. This is a division operation. My first operand is already in the accumulator, so I don't have to store it and get it back. So what we have reduced here is storing A plus B and reading A plus B. Those two operations are completely eliminated here. That's why I'm able to solve this problem with just 7 instructions. Okay, so program 2 and program 1, while they do the same thing, program 2 is a more efficient way of writing the same program to compute to evaluate the same expression, but more efficiently using fewer instructions. Very nice example actually. Okay, so there is one problem which we sometimes encounter when we have microprocessors with fixed length instructions. Imagine I have a microprocessor where my instruction length is fixed. Let's say my instruction length is 16 bits. Okay, let's just say that my instruction length is 16 bits. Fixed. It's a fixed length instruction, right? Now imagine this microprocessor has both 1 address instructions and 0 address instructions. Let's just assume. Okay, again I'm just taking a hypothetical example here. So let's assume in the 1 address instructions my opcodes are all 8 bits and my addresses are 8 bits. Cool. My instruction length is also 16 bit and my 1 address instruction perfectly fits into my fixed length instruction size. No problem. The problem arises when we have 0 address instructions also. See, in the 0 address instruction, the opcode is only 8 bits. But what about the second 8 bits? Because my instructions have to be fixed 16 bits. Because my microprocessor has a fixed length instructions of 16 bits. So the first 8 bits are the opcode, just like in your 1 address. So this is cool. What about the second 8 bits? In this case, what we do here is we apply this method called as expanding the opcode. Okay, what we do now is we have these 8 bits opcode. Here we can fill any 8 bit number. Any 8 bit number from 0000000 to 11111111. We can fill any of them. So instead of wasting these 8 bits, what we do now is we expand the opcode. We expand the opcode to use the whole 16 bits now, right? So we expand the opcode. So that's why this is called as expanding the opcode, right? To all the, to the whole 16 bits that we have, right? Let's see how it works with a simple example. Okay, we have this 8-bit example, right? So let's take an example, right? So suppose imagine, okay, actually let's solve a bunch of problems, right? That's the best way for us to understand this technique better. So expanding the opcode basically means for the one address instructions, I'm using only the first 8 bits for opcode and the second 8 bits for address. But for 0 address instructions, I could use the whole 16 bits to have the opcode, right? That's what it means. So the size of the opcode itself changes when you're expanding the when you're expanding the opcode, when you're using the expand opcode technique. So for one address instruction, the first 8 bytes could be opcode, but for 0 address instructions, the whole 16 bits, sorry, the first 8 bits here, not 8 bytes. The first 8 bits here is the opcode, but in the 0 address instruction, the whole 16 bits will contain information about the opcode. Let's actually solve a couple of problems so that we understand this better. Okay, so imagine I have an example like this. Imagine I have a microprocessor that supports 0 address instructions, right, and 1 address instructions, both. Okay, and let's assume my memory size is 16 words, right? Very simple question. My memory address is 16 words, which means my memory size is 16 words, right? Which means what is my memory address? My memory address is 16 bits. Okay, this whole thing is 16 bits, right? Because there are, my memory size is 16 words. I'm sorry. Since it is 16 words, how many bits do I need? What is 16? 16 is 2 power 4 words. So how many bits will I need? I will need a total of 4 bits, right? I'll just need 4 bits for my address. So my address consists of only 4 bits. Okay, very simple. Because my memory size is only 16 words. This is a very simple toy example. This is not a real world example. We'll see some real world examples in a little while. This is just for you to understand the expanding opcode technique with a simple example, right? So my address itself is 4 bits, right? Now so this microprocessor has fixed size instructions of 16 bits, right? As 6 bits, not 16 bits, 6 bits, right? So what is my instruction size? My instruction size is 6 bits. Okay, my instruction size here is 6 bits, right? My instruction size is 6 bits. Now it says my microprocessor has 2 one address instructions. It has 2 one address instructions. So the total number of possible 0 address instructions are. That's the question we are asked. Okay, let's solve this. This is very simple. So look at this. I have 2 one address instructions. First, let's look at it from the perspective of one address instructions. Okay, one address instructions. In one address instructions, my address itself will take 4 bits. So my address itself will take 4 bits, right? Which means I have only 2 bits for my opcode, right? Look at this. I have only 2 bits for my opcode, right? So this is my opcode and this is my operand address, right? This is my operand address, right? Again, we are looking at a microprocessor that supports both 0 address instructions and 1 address instruction. The memory address size itself is 4 bits, right? Which means I have only 2 bits for the opcode as far as 1 address instruction is concerned, right? How many 1 address instructions are there? 2 1 address instructions are there. So let's say if my first 2 bits start with 00 or 01, let's say, because I have 2 of them, right? So these 2, if my first 2 bits in the instruction start with 00 or 01, I'll consider them as 0 address instructions. And the next 4 bits, I'll interpret it as memory. These 4 bits, I'll interpret it as memory address, right? These 4 bits, I'll interpret them as memory address. Cool. Okay, so this is how my 1 address instructions look like. Which means, how should my 0 address instructions look like now? My 0 address instructions, because if the first 2 bits, look at this, I have fixed size instructions of 6 bits. So whenever I get, look at this, whenever I get a fixed size instruction, if the first 2 bits are 00 or 01, right, I'll interpret it as 1 address instruction. The control unit interprets this as 1 address instruction and it reads whatever data, whatever bits are here, the 4 bits that are here. The 4 bits that are here, it interprets them as memory address. Okay, and it says this microprocessor only has 2 1 address instructions, right? Which means the first 2 bits, which are 1011, they are not used by my 1 address instructions. They're completely left empty, right? Which means I can use them for my 0 address instruction. Now let's look at it from the perspective of my 0 address instructions. Okay, my opcode, my zero address instruction, because I don't have an address, I can use the whole 6 bits, right? I can use the whole 6 bits for the opcode, right? I can use the whole 6 bits for the opcode, just like what I've explained here. Here we can explain the whole 16 bits for the opcode. Here we'll use the whole 6 bits for the opcode. So the first 2 bits, if they are 10 or 11, the control unit interprets them as 0 address. And here I can have 4 more bits. Since I can have 4 bits here, look at this. How many values can I generate here? 2 power 4. How many values can I generate here? 2 power 4. So how many total 0 address instructions can I have? Look at this. My 0 address instructions have to start with 10 or 11. When it starts with 10, my control unit interprets this as 0 address. So it will not interpret this 4 bits as memory address. It will interpret this 4 bits as part of the opcode itself. Okay, because it clearly understands that when it starts with 10 or 11, it's a 0 address. When it starts with 00 or 11, it's a 1 address. Right? So now I have 2 power 4 instructions that I can create which start with 10. I can create 2 power 4 instructions that starts with 11. So total I can construct 2 into 2 power 4 0 address instructions. Look at this. These two are fixed. These two, I cannot use 00 here, because the moment I use 00, the control unit interprets it as a 1 address instruction. Right here, remember, here this whole thing is the opcode here, because there is no address. So the control unit first reads the first 2 bits, understands that this is 0 address instruction, so it reads the next 4 bits also, uses this whole thing as 1 instruction. So how many 0 address instructions I can have? 2 into 2 power 4. Here I have 2 power 4, here I have 2 power 4. So total of 2 power 5 0 address instructions I can have. In this, again, this is a very simple toy example, right? Let's look at a more realistic real world example now, right? So imagine I have a 32-bit microprocessor, right? So this is more realistic because 32-bit microprocessors are more in fashion, or they're more widely used today, right? And here when I have a 32-bit microprocessor, my word size, again, it says, again, if I have a 32-bit microprocessor, let's assume I've connected it to a main memory. So let's look at this, okay? So my main memory is 256 mega words. Because the size of a word is not clearly mentioned here, we'll assume that one word is 32 bits because it's connected to a 32-bit microprocessor, right? And how much do I have? 256 mega words, right? That's a maximum supported memory. So what is this? 256 mega words is 256 is 2 power 8. This is 2 power 20. So 2 power 28 words is what we have, which means the size of the address. Look at this. This is the maximum supported memory, right? So if I have 2 power 28 words that I can address, what is the size of the address? The address size is 28 bits, right? The address size is 28 bits. Very simple. Now it says this microprocessor has fixed size address instructions of 1 word. Because it's not clearly mentioned what is 1 word, we'll assume that because we have a 32-bit microprocessor, it's connected to a 32-bit word memory. So let's assume that this is 32 bits, right? So my fixed size instruction is 32 bits, right? 32 bits. Okay. This whole length is 32 bits. Let me just write that down so that we don't miss that. Okay. So it says this microprocessor has 8 one address instructions. It has 8. So what is the structure of a one address instruction? One address instruction will have opcode and the address. The address itself is 28 bits, right? If this is 28 bits, I am left with 4 bits for my opcode as far as one address instructions are concerned. Let's look at it from the perspective of one address instruction. In these 4 bits, look at this, I have 4 bits, right? In these 4 bits, I can have values from 0000 up to 1111. I can have total of 16 values, right? I can have a total of 16 values, 16 unique values here. Now, but it says the microprocessor only has 8 one address instructions. So what I'll do now is I'll break these 16 values into 2 regions or 2 parts. So let's break it into this, okay? So from 0 to 7, okay, these are 8 values. Then from 8 to 16, these are 8 distinct values. So the way we'll use it is if the first 4 bits are between 0 to 7, then it is a one address instruction. Then it's a one address instruction. So we can make our control unit interpret this as such that first it will read the first 4 bits. If the first 4 bits are between 0 to 7, okay, or 0000 to 0177, all the values in between, then it will be interpreted. Then this whole 32-bit word will be interpreted as a one address instruction with the first 4 bits for opcode, right? The first 4 bits are opcodes, right? Here I have 8 opcodes. That's what I want. These first 4 bits will be interpreted as opcode. The next 28 bits will be interpreted as address. Cool. So my one address is done. Now for my zero address instructions, I have the whole 32 bits. Look at this. I have the whole 32 bits, right? I have the whole 32 bits to represent my zero address opcode itself. I have 32 bit opcode now because I'm using the expanding the opcode method here, right? Look at this. So in the first 4 bits, so let's break this into 2 parts. First 4 bits, next 28 bits. In the first 4 bits, I can have total of 16 values, but 8 of those values are taken up by the one address instruction, which means only 8 more are left here. Only 8 distinct values. So let me not write 8 that way. So only 8 distinct values. These 8 values can be used here, right? So what happens is when the control unit sees the first 4 bits to be lying in this region from value 8 to 15, then it interprets this as a zero address instruction, which means it not only uses the first 4 bits, it will also use the next 28 bits. In the next 28 bits, how many values can I create? 2 power 28 values. So how many possible zero address instructions or zero address opcodes can I create? 8 distinct values in the first 4 bits, 2 power 28 values in the next 28 bits. So what do I have? 8 is 2 power 3, 2 power 3 into 2 power 28. So I can have 2 power 31 possible total. This is the unique number of opcodes that I can have in the zero address instructions, right? Because we're expanding and we are using the whole 32 bits for the opcode here. While in the case of one address instruction, only the first 4 bits are used as opcode, right? Very simple computation here. Let's look at one more question, right? One more slightly generic question. Imagine I have a microprocessor with both zero address and one address instructions. My fixed sized instruction is 32 bits. Cool. My memory is 128 kilowords. What is 128? 128 is 2 power, this is 7, this is 10. 2 power 17 words. Which means my address, again this is very simple. My address is 17 bits. So it says if n one address instructions exist, then the number of zero address instructions are. Okay, let's break the whole thing. Look at this. I have 32 bits here. My whole thing is 32 bits, right? This is very simple. With some practice, you'll become very good at it, right? My address, let's look at it from the perspective of one address instructions first, right? 17 bits for the address and 15 bits. I'm left with 15 bits, right? 15 bits for the opcode. 15 bits for the opcode, 17 bits for the address. Now, if n of these, so how many opcodes are possible here? 2 power 15, right? Of these, n are, look at this, of these, n of them are one address instructions. So how many zero address, how many of these 32 bits? Look at this. If you look at these 32 bits, if you look at this whole 32 bits and break it down into your 15 bits and 17 bits. Now, n of these 2 power 15 values are assigned for your one address instructions. So how many are left for zero address instructions now? 2 power 15 minus n. 2 power 15 minus n are left here. And now in your zero address instruction, we will be using expanding the opcode, which means 2 power 17 are possible here. So what is the total number of zero address instructions possible? 2 power 15 minus n into 2 power 17. That's it. Very simple computation. Again, all the 3 problems that we have seen are very simple problems. Again, I've shown multiple problems to help you understand the subtle details in how expanding the opcode technique itself works, wherein the opcode for zero address instructions is expanded to the whole fixed length instruction size. It's not just limited to the first few bits.